unlimited submissions. Awesome, I think that's it. Okay. Sorry guys, this is this lab is quite a scramble. Oh, .docs.pdf, awesome. So should be uploaded for you guys. Let's take a look. So today what we're going to do is we're doing hash tables. So if you open up your day 18 lecture notes, there's some starter code that you will be using for this lab. This is your day 18 lecture notes. And down here is your starter code. This will be your starter code down here. Now, let me do a more relevant poll, maybe. Do you understand hash function tables? Just want to see what y'all think. There's only 8 of us, so we'll see. Yes, maybe no. I just want to get a brief glimpse before I explain it, because I will explain it regardless. Where's my paint? There it is. Okay. Let's see if it shows up. Awesome. All right, y'all see this. So we get a lot of maybes and no's. Very few yeses. All right, maybe it'll click for you, right? So ultimately, what we want to design is some sort of container for data in which you can say something like, I want a hash table at, let's say, you can do anything. You can say a number. You could say, I know a lot of implementations allow you to do things like strings, like, right? And you can assign it to be some sort of value. And it could be, I guess, anything, right? So the idea is that you have a key that is mapped to a value, right? So in this case, the key is 23, the value is James, the key is friendo, and the value is 24. This is what we want to do. Now we want to do this in a very optimized and fast manner, right? We want to be fast, right? We want to be fast like Sonic. So in order to implement a fast and good and awesome and optimal hash function, we use a certain strategy that I will outline right now. So what we do to store key value pairs, at least with the implementation that I'm about to describe, is we will store them separately in 2 separate arrays. So let's say you have a keys array, and it's like this long, and then you have a values array that is the same length. Now, I'm going to describe to you a poor implementation. I'm going to tell you why it's a bad idea to do it this way. You might first think, how about we just put the keys in the array and just fill her up, right? So if you had the same thing, you had like, say key is, let's say we're using integer keys and string or character values, right? So 23 is going to be F, and then let's just keep going. 27 is A, 2 is B, right? You just keep filling this baby up We'll make this A again. Keys are unique, but values can be repeated, right? So in this way, you just fill her up and keep going until you run out of room. And maybe if you run out of room, you might have to resize or something. But let's not think about that. We don't care. That's not none of our concern. Let's just assume it never gets full. So this is a poor implementation, because what happens when you want to say, okay, I want to access the 24th item. Well, how would you find the 24th item? Well, you'd have to start here and you'd be like, okay, is this the 24th item? No. Okay. No. Is this one? No. All right. Is it this one? No. Okay. Awesome. Is it this one? Right? You see how maybe a little inefficient this is. Typically, when you have arrays, if you wanted to access the indices, right? You've got indices. If you wanted to say, I want to get the array value at 3, this operation is boom, instant. It knows exactly where 3 is. And therefore, this operation is order 1. It only takes one operation calculating the address of this value, and it's super quick. But with our totally inefficient hash function, this is going to be order n, because in the worst case, as if the array is length n, going to be iterating and doing some sort of operation n times in order to get that last item. Is that clear? I think that's clear. So this is a bad idea. We don't want to do this. Now, how can we design a hash function to be closer to order 1? That's our goal. We want order 1. We want that good stuff. So how do you do that? Okay, now let me suggest an alternative. Actually, let's just do this. Whee! What if we created what is called a hash function, and that hash function will take the key as an input and output the index at which that key is stored, right? So let's say you wanted to insert hash 24 equals j. What if we took 24 and we put it into our hash function? We said hash 24, and it output like 2. We would just say 2, we put 24, and we would put j, right? So they match up. It's the address, the index at which you put the item is calculated using this hash function, and you just put it there. So whenever you want to say, okay, what is hash at 24? This operation is order 1, because all you have to do is calculate this hash function once, and it will return you the address you want, and you just boom, you just go there. So anyone have any questions how that works? The hash function calculates the index, and there's no iterating, none of this garbage. We don't want any of that. No iterating. It just goes boom, address. Because we're storing this in an array, and any indexing an array is ordered 0, 1. So this is what we want. Now what we want is we want to design a hash function to make it so that the items just keep getting placed in the gaps. We just want to keep filling this baby up with items until the whole thing is full and there's no collisions, there's no overlaps. This function perfectly just sets everything in place. Well, that function doesn't exist. And I'm going to tell you a horrible truth. There's something called collisions. So what if I'm not going to tell you the hash function. Okay, maybe I will. Let's imagine a very simple hash function. If this array is size 6, right? This is the length of the array. Whatever hash function was just the key modulo 6. Okay, well, if we have h at 24, what's that going to be? It's going to be 24 mod 6. Now, I'm not smart enough to think about the answer to that in my head, so it's 0. right? It's 0. So in this world, we would put this item here at 0, 24, and we put, if it was j, we'd put j here, right? So that's what would happen, and that would be our hash function. Now, what if we also said h at 18 equals a? Now this would be an issue because 18 mod 6 is also 0, and you want to place 18a at the same exact location that you're trying to put the previous item, and this is what we call a collision. Blammo. How, right? No, don't like collisions. Now, in order to solve collisions are inevitable. There's no way to around it. There's no perfect function that will never cause collisions. So what we use is we use a rehash function. What we do is, if there's a collision, we will recount based on the current index that we're at. We'll take that index, so currently that index is 0, and we will do some sort of modification to it, some sort of rehash. So one very, very simple rehash function is taking it and just saying +1, right? So we will say, okay, instead of putting it here at 0, we're going to say +1, and we're going to move over one index to be here. So now what we're going to do is we put 8 and a. So perfect. We have stored the value in a location, and it is not overlapping anymore. No more collision. Bye-bye. We're happy. Now, wait. But it's no longer in the position that we originally hashed. How do we know whether or not 18 is here or 24 is here? Well, I'll answer you that question, right? Let's give it a shot, right? What if we tried to say, okay, I want to address hash at 24, right? So that's pretty simple. You just say, okay, we calculate the hash function. It's mod 6. The index is going to be 0, and therefore our item at 0 is j, right? That's super simple. But now we get to this problem where when we try to do the exact same operation to 18, we calculate the index to be 0, but you would think, okay, well, 0 is j. But what we do before we make that assumption is we check whether or not the keys match up. So we've got 18 here, and we check if that matches up with 24 here. If it does not match up, what we do is we do the rehash function. Therefore, what will happen is instead of just doing this, we rehash, we do +1, it's 1, 18 and 18 match up, bada bing, match. We found it. And therefore, hash at 18 equals a. Does this make sense to everyone? The way we know whether or not to run the rehash function is if these keys match up. And that's why we store the keys in a separate array. That's why we need 2, is that we need the first one full of keys to check whether or not we need to rehash whenever we index an item. And this just stores the item. Any questions so far? This is kind of the big brain moment where it all kind of comes together. So if it hasn't, like, your mind hasn't exploded by now, then let me know why it hasn't. It's not super easy, but once it clicks, it just clicks. I'm going to assume nobody has any questions. So if you do have questions, let me know later, and I can answer them. So with this knowledge, we know what a hash function is. Hash function gives you the original location that you're going to be indexing at, right? And the rehash function is if there's a collision, how do we recalculate the hash to update it to the next location? And in our example, we used a very simple hash function that just did modulo the length of the list. And we did a very simple rehash function that was just +1. Now, the question is, how do we design a hash function and a rehash function to minimize the number of collisions? I'll tell you, there's a couple things you can do to try to minimize collisions with a rehash function. So notice how in our past example, we had an array of length, is that 6? We had an array of length 6, right? And we noticed that anything that was divisible by 6 in our rehash function was equal to 0, and it would all be stored here. And so this is going to be a hotbed. A lot of numbers are going to hash into the 0 spot, but not a lot of numbers are going to hash into this spot. It's like a very low burning fire. So we want to design a hash function that will equally distribute the occurrence rate of the index equally across all things. So they're all equally on fire, essentially, right? We want a slow burn across the whole thing. So one way we can do this is, instead of using 6, if we're using a simple hash function like this, we can use a prime number, because a prime number is not often divisible by other numbers. And so it will be much rarer for it to be in this one spot, and it will be more equally distributed across the rest of them. It will not be quite as horrible here. It won't be like it was last time. So that's one thing that we can do, is we can design our hash function to use 13. And whenever you do any hash function, you're going to have to do mod 13, because you're not going to be able to store items past the length of the list. So you will have to, at some point, do mod the length of the list in your rehash function, and in your hash and your rehash function will have to take into account looping over. So that's one thing. Another thing we can do is, I can't say what the best hash function is, but I'm going to now start talking about the hash function that you're going to be using for your lab today. So the hash function that you're going to be using for your lab today, and if you look at the actual document, I have a little example, but I'm going to go over that example now. So the way we calculate the rehash function is, first, we take, if we're trying to find the hash of like 44, it's the example I use. Well, the way we calculate the hash is we say 44 squared, right? That's going to equal a number. Let me find what that number is. 1936. What? 1936. This is the result of 44 squared. Then what we do is we take the tens and the hundreds position, we extract that, and we have that be the next item. And then we take this item and we modulo the length of the list. And in our example, the length of our list is going to be 11. And this will give you the final result, which is 5, I believe. Is that true? I think. My calculator doesn't have a hash function. Trust me that this is the answer. If it's not, let me know. So this is our hash function here. So I'm going to write this as our hash function. So first you square it, then you take the middle 2, then you take, and then you modulo the length of the list. Now you might be wondering, what if we start with a really low number like 2? 2 squared is like 4. How do you take the middle 2 items of 4? Well, for this lab, we're going to assume that all of our keys are going to be greater than 10, just for convenience sake, because if it's greater than 10, 10 squared is going to be 100, and at least you'll have this here. So that's just part of the assignment. So now let's talk about the rehash function that you will be using. The rehash function you'll be using is a, what does he describe it as? He describes it as a quadratic probing. Right? And so essentially what it is instead of just saying +1 and then +1, and like when you have a list, you just keep looking for the next item until it updates over and over. This is really not optimal because it causes bunching, where a bunch of items are just right next to each other. So let's say you had a list of like a bunch of items, right? and you did one of the items shows up here, another item shows up here, and then you try to insert another item here, you get a collision. You try to insert an item here, you get another collision. You try to insert an item here, you get another collision. You try to insert an item here, you get another collision. You try to insert an item here again, you get another collision. And sometimes you get this range where if anything is inserted inside of this range, it'll arrive here. And so it creates these long chains of items. And this can be an issue because if you want to access this item here, you're going to start having to do a long iteration. And this is a very poor hash function because this will take a lot of time. So we don't want to group them together. We want to make it so that when you do a hash function, there's the least amount of rehashing necessary. One way to do this is quadratic. So instead of doing +1, +1, +1, our strategy will be +1, +4, +9, etc. So this is 1 squared, 2 squared, 3 squared, and so on. So each time you do another rehash, you will be doing, so if you have like I is equal to the number of rehashes you're doing, then essentially it's going to be I squared is your rehash function. So those are the two things that we're going to be doing is, I guess I can give you an example if you want. That's probably a good idea. So if you're trying to do, here is 5, 5 is 0, 1, 2, 3, 4, 5. You're going to do this location here. I should say it's J. And if you do a similar one, if you end up doing a collision, you'll say 5 plus 1 squared, which will be 1. So you'll get 6. 6 mod the length of the list will take you all the way back to the start. Maybe you put A here. And let's say we try to insert at this location again. Well, we'll do 5 squared, and that will take us to this A location. We realize that we have another collision. So what we're going to do is we're going to rehash again, and this time, because we've already rehashed once, we're going to do this, which will be 1 plus 5 plus 1 plus 4 is 10, and so on. And you'll recalculate with 10. This is not a great example because it ends up to be another collision. So and so on. You keep doing it until you don't get a collision. Have any questions on the hash function that we're using and the rehash function that we are using? No? Awesome. So I don't think I need this anymore. So I'm going to start sharing. Let's see what I want to do. Let's take a look at the lab assignment real quick. So what you will be doing for your lab is you will be taking the starter code here, and you will be editing the put and get functions, right? Put is assignment. So this is inserting an item into the hash table, and get is accessing an item into the hash table based on, so when you put, you're going to say, okay, I want to put something with a key and data, and then get is saying, okay, I want to access something, the data that is assigned to this key. So if you read through this code, you'll see that when you put an, let's say you get an item, right? Well, first you use the hash function, and while that, I don't think your screen is being shared, or maybe it's just me. I see my own screen being shared. Oh, it's showing up for Riley. I just see gray. I don't know. I'll wait for you guys. Okay, awesome. So what I was saying is the get function, it first calculates the first hash, and then this while loop takes care of calculating the rehash function and continually updating it. But this while loop won't execute as long as the hash function originally is perfectly fine. So, and then at the end, what it'll do is it will gather the data and return it. And similarly with put, it will calculate the original hash function, and it will then, it will insert the item if the hash function is valid, else it will start doing it'll calculate rehash and continually check if that rehash is valid, and eventually it will insert it in the correct location. So these two functions are probably the ones you primarily want to be looking at. And you will also be, I would assume you are also going to be editing the put and the get functions slightly. So if you look at hash function, this is the original hash function I was describing, which is you just take the key and you modulo the size of the list. We initialize the size of the list to be 11, and then we get the slots, which is essentially the array of keys, and the data, which is the array of data. You create it, initialize them all to be empty, and them all to be length 11. That's what this initialization function is. So it's going to be the key mod 11 in this code here. And then with the rehash function, you take the old hash, which was either the original hash or the prior rehash that also collided, and then you will take the size of the list, which is 11, and you will just do +1 to the old hash and then modulo the list. So that is the hash and rehash function. You will have to update the hash and rehash function to do our crazy little middle doobie, and this one you will have to do quadratic probing. One last thing, and it's in your assignment, it's kind of hard to notice, but here at the end says the only change that you have to make to the day 18 starter code is to change the very first H54 statement in the main program to be H52, because otherwise there won't be any collisions. Because our hash function and our rehash function are so good, there'll be very little collisions. And so it's important for you to test a collision. So you need to make this 52 rather than 54 right here. Very important. If you don't do it, we will take off. Otherwise, what you will do is you will submit your modified.py code, which will be very similar to the example code. And you will also include an output.txt, .docs, or .pdf that will have your console output. So we want to see this. We want to see this stuff, but we want to see it for the new hash and rehash function. So this will all these indices will be different. So if you look at some of the print statements, you say for key 54, right? So you're saying h at 54. And you're saying the hash function calculates that that data will be placed at 10, and the data will be cat at index 10 with the key 54. Awesome. So I think that's everything. Now that that is clear, I want to describe something that he probably tried to teach you in class, but maybe you forgot. So if you want to just work on the lab, now is your time to start. If you want to hear me talk about a closed hashing and open hashing, open addressing and closed addressing, stay tuned. So what we are doing in this lab is called closed hashing. And closed hashing is where you've got that internal list, and if there is And if you're like inserting an item, I'm just going to say this is the keys list. If you're inserting items, if you end up getting a collision, bonk, right? If you end up getting a collision, you have a rehash function. And so you just recalculate it to be a new location. Let's say it's here, right? That's closed hashing. It's when you have a single list, you have a rehash function. Open hashing is a little bit different. There is no rehash function. So rather than having a rehash function, essentially what you do is you'll have your list, say this is the keys list again, but each item in the list is the start of a linked list of items. So rather than having collisions and rehashing, you just store the item at the same position and you just append it to the list that starts at that address. That's it. And so the other terminology is when you have closed hashing, it's also called open addressing. So when you have this rehash configuration, it is called closed hashing, and you are using open addressing. So they refer to like two different concepts, but they're like closely tied together because they always exist in the same like location, right? They're always the same concept. Or the different concepts, they do the same, they apply to the same thing, right? So open hashing is closed addressing. So it says closed addressing because this one is open for rehashing, open for readdressing, but closed addressing means you're not going to change the address essentially. So that's the difference between these two things. One, open hashing is you're open to create this linked list, but it's a closed address, meaning it's the same address. But this one is closed hashing, but open addressing. That's when you have the rehash function. Awesome. So now I'm going to have another poll. All right. Get that student feedback, baby. And I can go around to anyone who has questions. And now I believe the lecture is over, as long as nobody says no. And if you say no, then hopefully it's something that we can address publicly. Otherwise, most maybes are probably very specific questions that pertain to them, I would imagine. Okay. Good luck, everyone. If you need an extra guide, you've got Geeks for Geeks at the top of your day 18 lecture notes, a little website that might help you. So that was a 40-minute lecture. Sorry for taking so long, but hopefully it's clear. You've got, what is it, 25 minutes left? I think, yeah, no, 35. All right, I'll let you guys chill and work it all out. Good luck. Sorry, guys. 4:20. I'm gonna come around to you guys. Anyone want to get any questions straight up, or otherwise we'll just pick some people. Okay, I'll just pick some people. Cool. understand the like separation conceptually of a node and how the nodes are connected and how they interact with add and delete and remove functions. Oh,
So
wait, we're
what?
all in the same room. We're in the main room all of a sudden. Hey guys, what's up? I think Mukesh pushed the delete function or something. Hi, Riley. Let me go remake the groups real quick. Man, I wonder how long I was talking. I was not looking. Like 5 seconds. Guys, I'm like really hungry. Did anyone bring a snack to class? Damn, no? Alright. Anyone got any other questions? Anyone I haven't come to? I haven't kept track of whom Rehash saw, so please, I have 9 minutes left of class and I'm desperate for company. I'm sorry. Uh, you keep exploding the groups.
Okay.
Alright,
I
let's do it one more time. Okay, well, lab is 1 minute over, guys, so if anyone's got any questions, let us know. But